Okay, we're just about to get started. Before we do, I wonder if there are any questions or concerns from the students that are here before we start with lecture and course material. Anybody has anything they'd like to bring up? Good time to do it now.
I have a question. How do you get the bathymetry map on Google Maps?
Yeah, all right, let me show you how to do that.
Thank you.
Well, I'm going to present some lecture material, and then I'm going to go through looking at Google Maps and guide everybody through like answering the first question in that homework. So that'll be an occasion when I do that. So let me not do that now. Let me do that when everybody can see. Okay. But it's just a matter of telling Google that you want to use the satellite overlay. Have you ever done that with Google Maps?
Yes, I was trying to get it to work, but I just didn't know how to get the final layer on there.
Yeah. I mean, it's astounding what Google does with these maps, but yeah, the ocean basin is it shows up as a satellite view, even though it's not really a satellite. Well, I guess some of it is a satellite view. Yeah, so I'll go over that when I finish the lecture, and then you'll have a few minutes. Hopefully, I'll get through this material about sediments, which is pretty straightforward.
I have a question about Sunday's milestone. Do we need to submit the overarching themes to go along with the proposal as well?
You should mention them or at least consider them. Yeah.
Okay. I don't know if we needed to address every single one of them. Or
no, you don't need to address every single one of them, in detail. But that should really, those overarching themes should really guide you in sort of deciding what you want to emphasize and what points you want to cover when you go to write your report and then make your presentation. And I think it's helpful. I've noticed that in the past when students have these assignments, it's sort of like, well, what do we cover? How do we relate this? And the idea of those overarching things was that here are ways of thinking about the material that you're going to uncover when you do your research. We can think about it in terms of scientific consensus, historical review, societal importance, and those give you a perspective on material that you can apply to composing your report and to choosing how you emphasize and what points you decide to bring out. Because of course, when you do your research project, you're going to be synthesizing multiple multiple research sources. And when you do that, when you've got 10, 12 different sources that you're trying to put together, you want to think of what are common themes that I can bring out among these different sources to tell a story with the information that you've gotten. Does that make sense?
Yeah.
Okay.
Thank you.
Sure. Okay, well, I guess everybody's here, 47. Hopefully more will join. Remember, it's required to join class, and we are recording. So this week we talked about ocean basins. Yeah, a question? Nope. We talked about ocean basins on Tuesday. And one of the things that I emphasized again and again is how much of the ocean is deep ocean. So how much of the Earth's surface, which is famously covered mostly by water, but of that water, the ocean depths are comprise, the vast majority of the ocean area. And so, and when we think about that hidden realm, it's characterized, pretty well everywhere by a cover of sediment. The exceptions being new volcanic material, new ocean crust. But even that new ocean crust is very quickly covered with a drape of sediments. And because the ocean basins are millions of years old, tens of millions, hundreds of millions of years old, and some portions of the ocean basin, sediments have had a very, very long time to accumulate. And we talked last Tuesday about how the stack of sediments builds up, year on, year out, over the millennia, over the millions of years. And that stack of sediments, is, first of all, creates the characteristics of the ocean floor as we know it. And then importantly, it gives us a window back into time for investigating what the Earth was like at different eras of sedimentation. So we want to look for we want to think about what sediments are, how they arrive, and then we'll be able to consider how to interpret those data. So, the big ideas are that ocean sediments are particles that sink through the water and land on the bottom. And the sinking and the distribution of particles is uniform over large areas, but there are regional and local characteristics that have to do with the source of the material and the types of materials that are settling. And I should say that the idea of sediment, a sediment is anything which can be moved in water or liquid. And so I don't know if any of you are wine connoisseurs, but you always store wine bottles on their sides. If you have fancy wine, I don't have much fancy wine, but if you have a fancy bottle of wine, you want to keep it on its side, and then every once in a while you want to rotate it, because what's happening in the bottle is that sediment is sinking out. Well, the sediment in a bottle of wine, of course, is very different from the sediment in the bottom of the ocean, but sediment applies to any particle which can be suspended in water and which eventually settles out. So when we talk about sediments, we're talking about a very, very broad range of materials. And so as we go forward here, we'll try to build up some big categories and understand how they are. So, and then very importantly, sediments deposited in the quiet seafloor provides a sequential record of recent events in the water column above. And so, when the sediments land, they carry with them information about the water through which they settled, and of course the origin of material that formed the sedimentary particle in the first place. And that as those sediments accumulate, we can drill down, core down, and then eventually drill down into the sediments. And by doing so, we can get a window into the past history of Earth. And so, much of what we know about Earth's climate and climate changes to the climate and characteristics of everything from evolution to species to the distribution of how much snow was falling, that sorts of things. A lot of that information comes from coring, from drilling into deep sea sediments. And sediments, I guess, are an important source of crude oil and natural gas. So sediments are oil and gas, hydrocarbons, are generated from organic material that's deposited in sediments. And then that organic material, when it's buried deeply enough, is heated, and under heat and pressure, that organic material is transformed into hydrocarbons, oil and gas, which present day are fueling our economy, our civilization. So understanding sediments is an important component of understanding where we get right now most of our energy from. Okay, so if we looked at core samples, and when I talk about coring the ocean, the drill ships go out and they drill into the ocean bottom, and they drill down hundreds, thousands of meters into the sediment, into the consolidated sediments that form the bottom of the ocean. And by recovering these materials, we can date what's going on. The age of sediments, of course, so the Pacific plate is transgressing toward the east, and it's coming up against the Indonesian plate. and the two plates are coming together and subducting down and forming these trenches and troughs, these very, very deep ocean regions of the ocean. Well, so this portion of the ocean basin is much, much older than the more recently generated area. So there's a seafloor spreading center here, and the new seafloor is spreading out. It's traversing across the very large Pacific basin. So if we think about ocean plates typically expand, and ocean, continents are separated at about the rate that your fingernails grow. It's an analogy that helps us understand how slowly this material accumulates over time. So if we think about, how long it would take your fingernails to grow from North America to the far eastern Pacific, far western Pacific, that gives you a sense of the time. So Jurassic and older, so this is 180 to 200 million years ago, early Cretaceous, mid-Cretaceous, late Cretaceous, Eocene, Paleocene, and then all the way into the more recent Pliocene and Pleistocene time period of the more recent sediments. So the basic message is that ocean sediments and the seafloor generally is getting older the farther you get from the spreading center, and that makes sense. But there's a really important principle here, which is that because of subduction, because the ocean plates are constantly moving and constantly being subducted either under continental plates or with other ocean plates, there is a finite time or finite limit on how old the ocean crust can be, and by extension, how old the sediments on that ocean crust can be. And so, generally speaking, the oldest seafloor is around 200 million years. So, and we know, of course, that the Earth is 4.7 billion years old, and the continents are, we've aged material on continents back at least 3.5 billion years. So the ocean crust is by extension a much younger phenomenon than the continental cratons and crusts. Okay. So we can classify sediments in a number of ways. We can classify them according to the material that they're made from. We can classify them according to their source and origins. But before we do any of that, we can just consider how large they are. So here's a rough and ready table, and this is from an earlier version of the Garrison textbook, but I think it's reproduced in all of the versions. And so this is describing the types of particles and according to size and giving them names. So the smallest particle are clay particles, and they have an average diameter of about 0.004 millimeters. And that's about 4 microns. 4 microns, a human hair is about 100 microns in thickness. So that gives us an idea that, clay particles are really, really tiny particles, very, very tiny components of sediments. And, a fundamental rule here is that the larger the particle by diameter, the more quickly it settles to the bottom. And it's a little bit counterintuitive, but it makes sense. So clay particles to settle, and this is the settling time to settle from the surface of the ocean to the bottom, assuming a depth of the ocean of 4 kilometers. So a clay particle can take up to 50 years to settle to the bottom. And there's a law, Stokes' law, that determines settling rate, and we'll get to that in a second. The next largest particle sediment category is silt, and that has a diameter. It's from the largest clay particles to about 0.062 millimeters. So 0.06 millimeters is still a very tiny particle. You could just barely see it. If you were looking at a single silt particle you probably see it under a microscope. Sand goes from the maximum size of silt to about 2 millimeters. And then there are granules, pebbles, cobbles, and then boulders. And so boulders are considered anything larger than 10 inches. So in the settling time, settling velocity, it's determined by ocean depth. So when you get up into the multi-millimeter size, Stokes' law doesn't apply to the same degree, and the settling velocity is harder to specify. Okay, so those are particle sizes and names of the different sizes. So the thing to remember is silt, sand, and clay, or clay, silt, and sand. These are the smallest particles, and most of the ocean floor is made up of silt, sand, and clay. So silt and clay and sand is largely confined to the coastal margins. So before I leave this, let's think a little bit about what this means. So if clay can remain suspended in the water for a very long period, years, and silt can also remain suspended in water for a very long period, whereas sand typically settles out within a day or so. What does this tell you about the kinds of materials that you would expect to find at different distances from land? In other words, how does distance from land tend to sort different particles by size? Any ideas? Anybody want to unmute their microphone and tell me what they think this would mean? It's also in the book, so you might have a notion.
Sorry. The larger sediments would be closer because they wouldn't travel as far.
Absolutely.
And then smaller as it goes along.
Right. So unless there's a local source, and we'll see in the case of hydrogenous sediments, and that there can be localized sources. So around hydrothermal vents, you can generate sediments that are much larger in size than silt or clay, but that's because there's a local source for that material. But absent a local source, the further you get from land, the finer, the smaller the particles are on the seabed. And by the time you get, 100 kilometers or more from land, most of the ocean bottom comprises clay particles. Okay? And the rate at which particles sink is controlled by this law, Stokes' law, and the components of Stokes' law are the velocity, and we multiply the velocity by 2/9 times gravity times the radius squared of the particle sinking, the relative density of the material, or the relative buoyancy of the material. So we get that from the density of the particle minus the density of the liquid. And so if we're talking about a negatively buoyant particle, this would be a positive number. A positively buoyant particle would be something that weighs less than water. So Stokes' law is mostly used to apply for sinking velocity, but it can also be applied to rising velocity. So in my work and Carrie's work, Carrie O'Reilly, we've had to consider not just the sinking velocity of material, but also the rising velocity of things like bubbles and drops of oil, because we've applied Stokes' law to understanding how quickly oil drops and bubbles of gas being released from an oil spill on the bottom would rise through the water column toward the surface. So we can take the principles of Stokes' law, and by changing the sign of this density, we can apply that to rising or sinking. Okay. And then you can see that the real driver in this is the radius. So radius squared pushes all these numbers up. So the larger the diameter of the radius of the material, the more rapidly it's going to move, the larger this V number is going to be. So that's Stokes' law. Now, Stokes' law is a theory or a law, and its velocity applies to spherical particles. So the assumption of Stokes' law is that everything that you're applying is a sphere. And of course, spheres are pretty rare in nature. So this is an approximation by default, but it nonetheless gives us a handle on the basic factors that are controlling this. Viscosity should be in here somewhere. Viscosity of the liquid, here it is, mu. So the viscosity of the liquid. So you could also use Stokes' law to consider how rapidly a raisin would settle in honey, for example. You could apply that same principle. You'd get an answer. How accurate it would be would be interesting to see. Okay, so the other thing to look at is the velocity of current versus the erosion rates of sediments. So water masses are moving around, moving across the ocean at constant, across broad areas. And so on this graph, we see on the x-axis the current velocity, the velocity of the water, moving water. And this is registered in centimeters per second. So we start with very small current velocities, approximately a millimeter per second, or a tenth of a millimeter per second, and all the way up to a meter per second. Now, just as a rule of thumb, and this is a good thing to sort of know, a speed of 2 miles an hour is about 50 centimeters per second. So 2 miles an hour is about the rate at which you walk. Most people strolling, unless you're power walking or really dawdling. But if people are just sort of walking around, 2 miles an hour is about how fast they walk. And that's about 50 centimeters per second. And that's also pretty close to 1 knot. So that gives you an idea there of how rapidly things move. Okay, so obviously stronger currents are going to be required to move larger items, and so on the left side of this graph we have sedimentation, which means that the material is settling out. It's going to eventually end up on the bottom. And on the right side of this line is erosion. So that means that the material that has been settled out and has formed some kind of sedimentary substratum, if the currents are strong enough, it will start eroding that material, and it's going to erode that material preferentially with the smallest particles first. So you can see that sedimentation of silt is going to occur all the way up to pretty strong currents. A 1 knot current, 50 centimeters per second. That's going to be enough to that would be considered a pretty strong current in the ocean. Most currents are less than that, and so sedimentation is going to occur all the way to sand and silt. But if you get into the stronger currents, you would get erosion. All right, is that clear? So whether or not a particle settles or whether it erodes after it's settled into a sedimentary substrate is determined by the size of the particles. And we can also classify sediments according to the source. Where do they come from? And here are a bunch of names that seem kind of fancy, but if you look at them, terrigenous, biogenous, hydrogenous, cosmogenous. And so these are, you all know terra, bio, hydro, and cosmo. And so that's, an easy way to remember what these different sources are. So terrigenous, let's start with that, since that's probably the most common. That's the erosion of material that is on land. You can also get terrigenous material from volcanic eruptions. So the clouds of ash and dust and particles that are released from a volcano, that material eventually can settle into the ocean and become sediments. Dust, that's a very important source of terrigenous sediments. And so, for example, the Sahara Desert in northern Africa is a source of dust, wind-blown dust. So strong winds across the Sahara lift up clouds of dust, and these dust clouds can be transported all the way across the Atlantic, and terrigenous sediments from the Atlantic can settle in the Gulf of Mexico, and do settle in the Gulf of Mexico. Examples of terrigenous material: quartz sand is probably the one that's most familiar to us. And so the the sugar sands of Pensacola, Panama City, those are material that have eroded from the mountains, from the Appalachians, the quartz minerals which are so prevalent there, and that material has been transported by water down rivers, and then deposited in the ocean, and then moved about in the ocean by ocean currents. Clays, estuarine muds, sands, terrigenous material is dominant on the coastal margins, on abyssal plains, on the polar ocean floors. Now, biogenous material is also a very important source of sedimentary accumulation. And organic material typically are hard parts from marine organisms. Now, you could have terrestrial organisms that might contribute sedimentary material, but those are far less common, rare in fact, compared to marine organisms. And there are two broad categories of marine organisms: calcareous and siliceous oozes. And we'll see, so the calcareous means that a form of calcium carbonate. Siliceous is silicate, and these are two different compounds, and they have different characteristics, which we'll get to in a second. But most, about 60% of the plankton produces calcareous, calcium carbonate shells, and the remainder produce these siliceous material, silicate material. And calcareous and siliceous oozes are dominant on the deep ocean floor. Below, and below about 5 kilometers, it's 100% siliceous ooze. So 55% of the floor is covered by that. Hydrogenous sediments, these are material that are formed by precipitation of minerals from water. And this can be driven by a variety of processes. We've already talked about hydrothermal vents. So hydrothermal vent fluid comes out into the water. It's anoxic and hot. And when it hits the oxygenated cold seawater, the material precipitates out. So there's a precipitate that forms immediately when the hydrothermal fluid mixes with the ocean water. So that's one form of precipitation. You can also get precipitation driven by bacteria. And so bacteria can cause the precipitation of manganese, phosphor, carbonate rocks. These can be precipitated with the facility of bacteria. They're pretty rare, less than 1% of the ocean floor. Now, the final category is cosmogenous. And this is dust from the space, meteors, and that family of materials. And that's pretty rare. Doesn't cover any significant amount of the ocean floor. Nonetheless, it's possible to find tektite spheres and glassy nodules that originate from space dust and meteors, and they do occur in the ocean. Very small materials. Okay, so this is a classification of sediments according to type and source, and we've given names to these. So, most of what you're going to be considering in this class is going to be biogenous sediments, and we'll think about a little bit about terrigenous. And then hydrogenous is important for considering the impact of bacterial action and hydrothermal vent precipitation. Okay, so here's a picture just to illustrate some of these factors. And we're seeing a lot of things. So this is a picture that I took with a deep sea camera in the Beaufort Sea, which is in the Arctic. And this picture was taken at a water depth of 1,800 meters at a distance, I think this is around latitude 55, latitude, something like that, pretty far north. And we're far from land. We're about 700 kilometers from Barrow, Alaska at the time this picture was taken. So what do we see when we look at this? Well, the biggest picture is this, this sort of ochre, gray, green material. And this is ooze. This is a clay-rich, silicon, silt-rich material, and it's settled out on the ocean floor. And then as we get closer, we can see that there's a mixture of this white material. You can see a lot of sort of white particles, and some of these particles have, distinctive shapes. Well, a lot of that is our biogenous sediments. So these are the shells of planktonic organisms that have died, and then their shells have settled to the bottom. And the current regime around this little boulder creates a sort of turbulence that preferentially causes these shell materials to settle closer in. And then we see on the boulder itself here, so let's see, there's one green dot here, and then there's another green dot here. These two green dots are 10 centimeters apart. So we get an idea that this boulder is in itself about 30 to 40 centimeters in this direction, and maybe 30 in this direction. So you wouldn't consider it a boulder, and if you saw it out in the wild, in a park somewhere, you'd probably think of it just as a big rock. But in terms of our classification scheme, this qualifies as a boulder. And so what do we see? With this boulder, we see that there are all kinds of organisms encrusting on this. There's some kind of a little tunicate here. This is maybe a bryozoan or an octocoral. There are polychaetes that have formed tubes here, barnacles, and then there are amphipods swimming around this. And this is the case. This is a common phenomenon in the ocean, which is that organisms tend to be attracted to structure. And there are a couple of reasons, for this. For organisms that are sessile organisms that need to attach to a hard substrate in order to grow up and reach maturity, the presence of some kind of structure gives them that substrate to settle on. But then there's also this phenomenon of, as soon as there's a community formed, other species can gather around or cluster around that community and achieve benefit or derive benefit from the association with other organisms. So there are amphipods swimming in the water, and then there's a little shrimp here. So that's a boulder transported. Now, I said we were about 700 kilometers from land, and then here we have a boulder. And of course, alert students will say, but wait a minute, you said that boulders and big sediments are only found close to the land. So that being the case, how do we think that this boulder got 750 kilometers from land? Any ideas?
Glacier.
Glacier. Well, you're close. It's actually not glacier. What it is that ice, sea ice forms, and when it freezes on the bottom, it can freeze around rocks and then float and drift out into the open ocean. And then when the ice melts, as it does seasonally, the boulder will drop off and sink to the bottom. So you actually get quite a number of transported boulders or rock material in the middle of these areas. But they're, I say there's numbers, they're common enough. So driving along with our deep sea camera, we would see these occasional rocks and boulders, and they were not uncommon, but most of the seabed is this clay ooze material. Okay, so I'm identifying these white structures as being calcareous plankton, and I'll show you an example of what that is. But how do we have to introduce a really important concept here. And this is the concept of the calcium carbonate compensation depth. And the calcium carbonate compensation depth is a broad demarcation across the ocean, and it's determined by the alkalinity and the pH of ocean waters. And here's what you need to know at this point. So the alkalinity, or the pH, the acidity of ocean water, is largely determined by how much carbon dioxide has been dissolved into and suspended in the water. So when carbon dioxide is dissolved in water, and the source of the carbon dioxide is largely the atmosphere, it dissociates, and one of the dissociation products is carbonic acid. So the presence of CO2 can make ocean water, or does make ocean water, slightly acidic. And this is something that we've all experienced. If you make soda water with a CO2 tank and I don't know if any of you have I've got one at home, what are they called? I forget the name, but you make your own soda water. You put in a big tank of carbon dioxide, and then you have special bottles, and you spritz the carbon dioxide into the water, and it makes carbonated water. And you'll recall that carbonated water has a slightly sour taste, slightly acidic, and that carbonation and that acidity results from carbon dioxide, which is dissociating in water to form carbonic acid. All right. So one of the chemical principles is that temperature and pressure allows a greater degree of CO2 dissolution in the water. So CO2 saturation increases with lower temperature and higher pressure. So if the CO2 saturation is increasing, if the amount of CO2 in the water is increasing, that means there's more dissociated carbonic acid. So that means we would expect, according to this principle, that the deep waters would be more acidic than the shallow waters. And that's the case. And the demarcation here is the degree of the level of pH which will either dissolve or allow calcium carbonate to accumulate. So typically the CCD, calcium carbon compensation depth, is at about 4,500 meters. In the Gulf of Mexico, it's actually a little shallower. It's at about 3,000 meters. And so above that line, if any calcareous shells and settle to the bottom, they remain there. But below that depth, the calcium carbonate tends to dissolve over time. So the CCD, and you can think of it, I suppose, as a snow line on the mountains. That's kind of what they're showing here, so that the ocean bottom, when it sticks up high enough into the water column, gets above this CCD, and calcium carbonate can accumulate. Below the CCD, the calcium carbonate tends to dissolve. So this, and that has a direct effect on what kind of biogenous sediments can accumulate. And I said there were two types of sediments, calcareous and siliceous. And calcareous sediments are, this is an example of a calcareous sediment. So this is a foraminiferan. And actually this foraminiferan is taken from sieved out of mud samples, taken very close to that boulder picture that I showed you a few minutes ago. So this is an example of a calcareous a marine organism and its shell. And this is pretty large, you know, it's almost a millimeter across. And a lot of the planktonic organisms are going to have smaller shells, but this is the same process. So in shallow water above the calcium carbonate condensation depth, this kind of a test shell could persist, could accumulate over time, and that's what we see in the boulder there. You know, there's these white things, and some of them are foraminifera. And others are, I'm not sure what all of the different sources are, but those white materials there, those white particles are calcareous sediments or calcareous particles, which can persist at 1800 meters because that's above the calcium carbonate depth. All right, I don't think this movie plays. Unfortunately, I've lost this video, but it shows current moving across the bottom, and you can see particles being suspended, and you can see the larger particles are moving more slowly than the bigger particles. So there's the calcareous ooze, and then the other class of organisms are siliceous organisms, and there are various types, radiolarians and diatoms being the most common siliceous silicate-based organisms. The radiolarians make these beautiful, complex silicate glass-like structures that they live in. Diatoms, I guess I don't have a picture of a diatom here. Diatoms are, they tend to be, they're two shells that sort of fit together like Tupperware pieces. And the organism lives in the middle of the two shells, the two tests. And then upon death, the tests remain. And so because calcium carbonate dissolves in the deep water, when you get far from land, all of the material that accumulates are the siliceous particles, silicate-based particles, glass-like particles. And so they tend to be very, very fine, very small inside. The particles are very small in size. And so what you have, if you have an accumulation of a volume of this deep sea sediments, is what's called an ooze. And this ooze can be described as calcareous ooze or siliceous ooze. And so in the deep ocean, most of the seafloor comprises siliceous ooze. So thousands and thousands, millions of square kilometers of siliceous ooze are what lie at the bottom of most of the oceans. And hydrogenous sediments, I said they were different types of hydrogenous sediments. And so here we're looking at a large accumulation of orthogenic carbonate. And so this is a carbonate, like calcium carbonate substratum. And this is formed, this is in the Gulf of Mexico. This is at a depth of about 550 meters. And this rocky body that sticks up probably about 7 or 8 feet above the bottom. So it's a pretty large, prominent boulder. This rocky material was formed as a result of bacteria and bacterial consumption of hydrocarbons. So this site is a place where there's natural oil and gas being released first into the sub-bottom sediments and then into the water column. And the oil and gas in the sediments is attacked by various microorganisms, bacteria and archaea, and those organisms, in consuming the carbon from hydrocarbons, as a byproduct, they form calcium carbon dioxide, and then this carbon dioxide can accumulate as calcium carbonate. So this is an example of a hydrogenous sediment formed by microbial mediation at a location where there's natural hydrocarbon seepage. And then you have corals here. So these are soft corals, and these are hard corals. This is a stony coral called Lophelia pertosa, and this, these are calcareous organisms. So the skeletal substrate of corals is calcium carbonate, and so when this organism dies, this coral is going to be left behind. And so corals are also a source of very large accumulations of sedimentary material and seafloor substrate. Another example of hydrogenous sediments we've talked about a couple times are hydrothermal vent fluids. And so here you can see this is Juan de Fuca, picture taken at a hydrothermal vent on the Juan de Fuca Ridge. We've showed you some pictures of that already. And then this is this smoky particle, this smoky material here. This is the hydrothermal fluid that's coming out, and the smoke is caused because the polymetallic sulfides are precipitating out of that fluid as soon as it sees oxygen in cold water. But this material is going to settle out, so the seabed all around this site is sedimented with this hydrogenous sediments formed from the hydrothermal vent fluids. And then, of course, there's lots of biological material that's formed. Yes? Question? Go ahead. Is there a question? Okay, SodaStream, yes. All right, so that's hydrogenous sediments. And just, another sort of distribution and sort of classification of sediments. We distinguish between neritic and pelagic sediments. So neritic sediments are material that's basically settles right out. This is has an average thickness of 2.5 kilometers, close to the continental margins. And then there's pelagic sediments. So pelagic is a word we're going to encounter many times in oceanography, particularly when we're talking about organisms. And pelagic means free swimming or transported by currents. So pelagic sediments implies sedimentary material which has been transported by water currents. Okay, so the continental slopes, rises, and deep ocean floor comprise pelagic sediments and account for something like 90% of the ocean area. Continental shelves, about 9%, 10% of ocean area, comprise neritic sediment, terrigenous material. So sediments can accumulate to great thickness on continental margins. Shelf sediments can be converted into sedimentary rock. So as these sediments build up deeper and deeper and deeper, they pack together. The weight of the sediments accumulating on top causes the sediments to consolidate, and eventually the separate sediments are joined together in a cement-like fabric that is essentially a rock. And so sedimentary rock, if you go, it's usually about 100, 150 meters when below the sea floor that all the sediments are consolidated into rock-like materials. Okay, carrying on sediments in the deep ocean basins. How do we classify those? We talked about oozes, two classes of oozes: siliceous ooze, calcareous ooze, hydrogenous sediments we've talked about a lot. Turbidites, these are deposits made by turbidity currents. I talked a little bit about turbidity currents on Tuesday when we were talking about marine canyons. And when a underwater mudslide starts flowing, that's referred to as a current of water. So one of the reasons that currents can flow for long distances underwater is that the water lubricates the moving sediments and it helps to suspend it. So a mudslide underwater can travel for much longer distances than a landslide in a mountainous area on land would travel. On land, the frictional forces of the acting on the particles that are sliding, slumping, pretty quickly stabilize into a solid and stop moving, whereas turbidites can go for very long distances. So turbidites, so that process could move neritic material from the coastal margins all the way into the deep ocean if there were sufficient and localized turbidity currents. Hydrogenous sediments, chemical reactions that occur in existing sediments. Evaporites. Evaporites are an important class of sedimentary material. And essentially what they are salts that are formed when the ocean dries out and the ocean evaporates. And this occurs, and geologically, it's pretty common, and also occurs in the present day. So there are places where the ocean has been flooded into an area, and then for whatever reason, it's cut off from the rest of the ocean, and there's not enough supply of water to keep it liquid. The water evaporates away, and what's left behind are the dissolved solids, mostly salt, that was present in the water. So that process, so those materials are called evaporites, a mineral formed by evaporation. And evaporites, as we'll see in subsequent lessons, can be an important component of deep sea sediments. And a little bit more about ooze. So calcareous and siliceous oozes, I think we talked about that. So move on here. And evaporates and precipitates that form as water evaporates. They include salts with economic importance. And we get evaporites in the Gulf of Mexico, the Red Sea, the Persian Gulf, the Caspian Sea. These are all places where we have evaporites forming. And so here's a distribution that sort of like just maps out and summarizes a lot of the things that I've been saying. So the continental margins, these are this light colored continental shelf areas around, the major continents. And this is going to be mostly neritic material, thicker, a lot larger particle size. And there are glacial deposits. But you can see that, that much of the ocean is, are these different oozes, calcareous and siliceous diatom oozes. And so, large swaths of the ocean floor comprise these oozes. So what do you see if you compare the Pacific and the Atlantic Ocean? You can see that the Pacific has much larger area of clays, so there's much less transport of material, of neritic material into the deep ocean in the Pacific than there is in the Atlantic. Well, okay, so that's a tour of the sediments, and that's kind of what I, sort of an overview of the material covered in Chapter 5. And I want to close by looking at some of the ways that we study ocean sediments. And I'll start with deep sea cameras, clamshell samplers, piston cores, core libraries, sediment profilers, and sediment traps. And so I'll go through each of these briefly and give you an overview of the kinds of instruments that oceanographers and marine geologists use when they're sampling and then ultimately investigating, analyzing sedimentary samples. So one of the devices that we've used is the deep sea camera. And I showed you an example of a picture taken with a deep sea camera, and I'll show some others as we move along here. So this is a deep sea camera on the German ship Zona, and this is the sled that this thing is lowered down on. This is a particularly massive deep sea camera system. German ships like to do things in big, robust packages. And so this has got a bunch of different things going on here. These are electronic control devices. Of course, this is going down very, very deep. I think they have, I think on this ship, they had something like 6,000 meters, not 6,000, more like 4,000 meters of cable. So they could lower this device down quite deep. And of course, when you get deep in the ocean, the pressure builds up. And so if you want to keep something dry, you have to put it into a container that's very heavily thick-walled and reinforced. And so these cylinders up on the top layer here, these are electronic control cylinders, and there's some batteries as well. Other devices, this is a CTD here, conductivity, temperature, density sensor. This is a ocean sensor, which we'll talk more about when we get into the ocean structure questions. And so this is a device which measures the temperature of the ocean, the pressure of the water, and the salinity of the ocean water. And it does so on a real-time basis. So you get a readout of what the water characteristics are at different depths. And this is very important. Using a CTD is very important for profiling the ocean, for trying to understand how a depth, temperature, and salinity change with depth. Okay, but then on the bottom of this device is the OFIS, by the way, Ocean Floor Observing System is the acronym that the Germans gave to this device. And we got a bunch of other devices here. So here's a digital camera. This is a digital camera of my design that we put on. And here was a strobe. So we have to, the deep ocean is entirely dark. So if you want to take pictures of anything, you have to provide light. This is a still camera, so it's taking a picture every digital still camera. So it's taking a picture, I think we were doing this every 30 seconds or something. So every time a picture was taken, it would synchronize with the strobe, so there'd be a bright flash of light, and that would allow the camera to expose. There was also another strobe in video cameras, real-time video cameras up here. And so this is the video camera, and these are film and video cameras that are, and here are two more lights. So these lights provide continuous light that allow the video camera to capture. What else is going on here? There's a couple things. This is an altimeter, Benthos altimeter. So this is sending out an acoustic pulse and giving a continuous readout of how far the OFIS platform is from the sea floor. And so that's really important, that you can't tell how far something's down. So this, I think we were operating this camera in about 3,000 meters of water, so very, very deep. So you can't see what the platform is doing, but you don't want to run it into the bottom. And so there's a continuous readout, and then there's also this weight hanging down. I think this is a 2-meter line. So this weight is hanging down below the platform, and it shows up in the pictures. You'll see it here in a second. And so, yeah, let's switch over. So here's a picture taken from this OFIS system. This is a still camera picture. Can't remember if I took this with the digital picture or not. Here are two laser dots. And laser dots show up a lot when you're doing deep sea photography because it's hard to know the scale of things. So in order to tell how big things are, you have to have some constant source of scale. So the way that we cope with this is we take two laser beams, the laser pointers, we put them in an appropriate deep sea package, and then turn them on, and the lasers are mounted in parallel at some known distance apart. So we know that if the lasers are mounted 10 centimeters apart, that the two dots are going to project a 10-centimeter span on whatever bottom they're hitting. And so this gives us a scale of objects. And then here's that lead weight that we saw hanging down from the bottom of the office platform. So the way this deep sea camera system is operated is that the ship either drifts or very slowly motors across the water, and the camera records what's going on. And there's an operator who controls the winch that has the cable out. And if the operator sees this weight getting too close to the bottom or rubbing, hitting the bottom and creating clouds of sediment, you reel in on the winch to lift the platform up a couple of meters and get it out of the way. And likewise, if they're too far from the bottom, so you can't really make things out, you can let out cable and bring the deep sea camera into closer position. And I'll also say that when you're taking deep sea pictures or doing deep sea camera surveys, what you're seeing in this picture here is about what you see everywhere. So there are vast areas where there's really a few. So there are a few burrows, and some places you see more burrows than elsewhere. Here is a single stalked organism. A lot of these things we don't even really put a name on. But the point I'm trying to make is that this sort of monotonous, uniform sedimentary drape is everywhere. Okay, so I think we're gonna switch here now. Next. I hope this plays. No, this is not playing. I want to show this. I'll stand by a minute. I'll try to find this video and show this to you. So I'm just looking for this picture. This is a picture of using that same camera system. And in the process, we discovered, let's see. Oh, well, looks like I'm not going to be able to show you this video. Too bad. I'll find it and bring it out. This is kind of a cool discovery process. So hold that thought, and we'll look at it later. Okay, so transforming from taking pictures of the sediments to actually sampling them, there are a variety of methods. And one method is what's called a piston core. And what this is what the intention here is to collect a core of samples. So what's a core? Core is a cylindrical sample that can be 1 meter, 2 meters, 3 meters. And they're jumbo piston cores that can collect as many as 20 or 30 meters of sediment. And so the way this works is this is hollow tube, often with a sharp end, and a weight, heavy weight, and that's lowered down and then driven into the sea floor. And there are a couple of ways of doing this. You can either lower it down with a weight, it's called gravity coring, or you can employ piston coring. And the way piston coring works is that there's a trigger that holds the weight and the core onto a cable. And then when the trigger hits the bottom, the cable is released and the pipe falls to the tube, the core barrel falls through the water and hits the bottom. And the length of this cable is adjusted so that as soon as it hits the bottom, there's a piston here at the bottom. And then as the core sinks into the bottom, as the core barrel sinks into the bottom, the piston is withdrawn, or it advances past the piston. And the reason that you do this is because that suction allows you to get a longer, more intact core than would be possible if you were simply driving an empty core barrel into the bottom. So this piston coring is a common method for sampling sediments. Now, of course, the sediments that you sample with this are going to be unconsolidated sediments. To get rocky cores, you have to use a drill bit, and we'll talk more about that in later lectures. Okay. Well, we talked about sediment traps and sediment trapping, and we talked about sediment settling. And so when sediments settle, the rate at which they're settling and the characteristics of the material with the particles that are settling can be important for understanding different ocean processes. And so what I'm going to show you here is, so if you wanted to collect some of this material, some of these sediments that are settling, you'd have to have some kind of a trap or some kind of a device that would allow you to collect this material. And what you might imagine is that you'd have some kind of funnel facing upward, and that as sedimentary particles rain down on that funnel, they would be collected. And so what I'm going to show you here is a deep sea mooring. Hopefully this plays. Oh, come on. Well, okay, here we go. Now it's playing. There we go. All right. So it's sitting and there's this huge weight. This is actually a train wheel. We're looking at this from the submarine Alvin. You can see the porthole here. This is the chain that's holding the bottom of. This is a mooring. So we're going to go up quite a distance on this mooring. This thing here is an acoustic release. So this is a special device that's got a hook here that can be opened under command, so that if you want to recover this material, you send a signal to that release, and it lets go of the anchor. Okay, so we're going up, flying up on the water column here, and we come to the sediment trap. And so here is the sediment trap, and these bottles here are on a rotating carousel, and they are positioned underneath this funnel. So sediments land on in the funnel, they settle down in the funnel, and they're collected in these little bottles. And then a device rotates the bottles underneath the sediment trap. And so knowing the rate at rotation tells you when the sample is taken. This is a current meter here. So this is measuring the currents, important for understanding how things are settling. And we keep going up the cable here. So we just saw the sediment trap there, moored probably 10 meters above the bottom. And we're continuing to fly upward in the on the cable here, and pretty soon you might ask, what's holding this cable upright? Well, it turns out that we have a very complicated flotation system. Here is the first of many hard hats. This is a plastic protective coating, and in each of these hard hats is a hollow sphere, 50 centimeters in diameter. And the sphere contains air. It's glass. The glass is about almost half an inch thick. And that hollow sphere of glass being very strong, is one of the few flotation devices that you can use in the deep ocean. Each one of these floats has a lifting capability, a buoyancy of about 50 pounds. And so this whole array, this whole collection of about 8 different floats is needed. So here we are at the very top. So this mooring will have been put out from a ship, will have been dropped to the bottom. It will have been set out for some period, a year, 18 months. And all during that time, the sediments will be collected in that, they'll settle in the funnel, and then the individual samples will be collected in those jars. The jars rotated underneath the funnel, so you get a monthly or biweekly indication of, or sample of the sediments that have settled out of the water column. So that's a sediment trap mooring. And what else do I want to talk about? Talk about landers. Here's another form of sampling the seafloor. This is another device that I've used. So here's a lander being put down, and you'll recognize these hard hats. So this is again the glass sphere flotation. Here's a current meter. Here's a camera sphere. And then this is a camera that is built to take a picture and then rotate 36 degrees and take another picture. And so, what we did for this little experiment was we lowered this lander to the bottom, and we had some kind of bait in this cage here, and we left it down for a few hours, and then we could see all of the eels and worms and other fish arriving to feed on the bait. So these are all pictures taken from that camera as it rotates around. So this is a way of observing activities taken on the seafloor. Another means of sampling, I got a lot of pictures from this German ship here. This is a grab sampler that they use, basically like an old-fashioned steam shovel, and they lower this thing down. Those two things close together, and it brings up samples. And so here's a sample of oil. This sample was taken from a natural hydrocarbon seep. And so this is an oily rock that came up. And then here, one of the scientists is having a fun time collecting the samples. What else have I got here? Oh, this is multi-core sampling. So this is a different type of sampling. This is largely used for biological and chemical oceanography. So this is a device. It's got multiple individual cores, and it's lowered down from the surface. When it hits the bottom, there's a weight that releases, and all these cores are pushed into the sea floor. And then when the device is recovered, it lifts up, and then these covers swing down. So they swing down like that. And so here you can see before the core sampler, a multi-core, these are called, multi-core went in the water. And then here they are, they come back on deck, and all the students are out busily collecting these mud samples. And what they'll do is they'll sieve them out, sort out, they'll take samples of the sediments for chemical analysis, and then they'll carefully sieve out all of the organisms that are living in the sediments and use those for studying biological processes. So that was a quick overview, historical information, location, natural resources, and a summary. Marine sediments are important historical records and a site of natural resources. We study these using different methods, including core samples. And here's the approximate age in thousands of years. This is 018, so this is one of the isotopic signatures that we can use to measure temperature. And so, looking at ocean temperature backward in time from core samples is one of the ways that we understand, how Earth's climate has changed over time. All right, well, that's as much as I had. Oh, I guess we didn't get into the, let me do one other thing while we're here. You have for your homework assignment you're assigned to look at the ocean. And so I'm going to share my screen. And share again. So here's Google Map. Okay, so what your assignment for the team homework is to look at the ocean and try to locate different sorts of features in the ocean. First thing you have to do on the lower left here is a little icon called satellite, and you turn that on, and it shows you, satellite overlay of the entire globe. And this is a pretty amazing feature of Google. I mean, you can zoom in anywhere, so you can zoom into the rainforest and in the Amazon and see, different features of that. But in the ocean, we're looking at satellite bathymetry. So this is bathymetry calculated from the different satellites. And so this gives us a picture of what the ocean floor looks like across the entire globe. And so your exercise for this week is to go through this and use the information that we've presented in the course and that you've read about to try to identify different features. And of course, the feature that you see right away is this mid-ocean ridge running down the center of the Atlantic basin. And so this ridge is the source of new ocean crust, and the formation of this new ocean crust is the process which has first of all rifted apart Pangaea, and then over time separated the continents of Europe, Africa from South America and North America. So if we zoom in on this mid-ocean ridge, we can see that there are these faults which run approximately perpendicular to the axis of the ridge. And these are the transform faults that we talked about, transform faults that are that form because they're accommodating the movement of this rigid, brittle crust over a spherical surface. And so for your assignment, you have to go through and find different features. So here, for example, is a trench with a back arc basin. And so that's one of the things that you're going to have to find in the homework. Okay, any questions?
I have one, but people can leave for me to talk about it. Yeah, if they want to. I had some I was curious about that map of the distribution of the different sediments.
Yeah, sure. That I showed in the lecture?
Yeah.
Okay. You want to go back and look at that? That's like the one I showed first off, or the one that I showed the global ocean distribution?
I think it was the global ocean distribution.
Okay.
Well,
I'll show that, but before I do, if anybody has any questions about the assignment or other questions, if not, I'll go back to sharing that.
I have a question about the assignment.
Okay, yeah, go ahead, Sarah.
If we use any kind of sources to help answer these, should we include those?
Yeah,
Okay, thank you.
yeah, it's always a good idea to include your sources. And, it's a good idea for a lot of reasons. It's a good idea because it helps you avoid, plagiarism. It's also a good idea because, if you're doing research and you find some good bit of information and you write it down, well, you can spend hours, days later on trying to go back and figure out where you got that little piece of information. You can't really use that piece of information in formal academic writing unless you can cite your source. So it's always a good idea to get into the habit of, whenever you find some noteworthy piece of information that you want to use to answer a question on an exam or homework, or to, use in a report that you're compiling, write down where you got it, in your rough notes. And then when you go to, compile your bibliography, you'll have that information right there. And that's how you avoid plagiarism. That's also how you can remember where you got important information, so you can go back and get more from that same source. Any other questions? All right, well, let me go back to that map and try to answer the question. Let's see. This is the map. This is the map you're talking about?
Yeah, that one.
Okay, what can I tell you?
I'm just trying to understand what makes like specifically between the Pacific and Atlantic Oceans, like what makes those like the composition of those like seafloor sediments so different. I feel like the mid-ocean ridge would have something to do with it, or maybe the like the Atlantic, like that, I forget what it's called, you know, the current that circles that really big dead zone in the middle.
The Gulf Stream,
Yeah, the Gulf Stream.
right.
Like basically why is there so much like calcareous oozes in the Atlantic versus mostly clay in a lot of the Pacific in the northern hemisphere?
Okay, well, one reason is that the rates of productivity are higher in the Atlantic than they are across most of the North Pacific. And so this region up in here, you know, has relatively low levels of productivity. So you get less, and this is also much deeper. So you get less calcareous. It's too deep, so it's below the calcium carbonate compensation depth. And so calcareous material doesn't accumulate. And there's relatively less siliceous and productivity by diatoms and radiolarians. It's also
And-
older.
Sorry.
Okay.
And is the in the Pacific Ocean, or I guess at least around the poles, I guess, is that water a lot deeper, and is that why there's a lot of siliceous like oozes?
Yeah, this is deep water. This is also a highly productive region of the ocean. So, you know, the Southern Ocean has got very high primary rates of primary production. So there's a lot of planktonic biological activity, and so there's a lot more. So this is a combination of deep water and high ocean productivity.
What's the reason for all the productivity at that part of the ocean?
Upwelling. So there's upwelling deep water. So we'll talk about upwelling processes, I think, next week. And so upwelling is the process by which deep ocean water comes to the surface of the ocean. And that's a really important process because the ocean tends to be nutrient poor. And the deep ocean tends to be nutrient rich. So if deep water comes into the surface, it provides nutrients, chemicals necessary for life, to marine plankton. And the Southern Ocean is a region where there's very high upwelling, lots of upwelling. We also get a lot of upwelling off the coast of South America, so there's upwelling in here. But and I don't really have a good explanation for you why you have these high clay levels. Well, I guess the clays here are a result of erosion of the Andes mountain chain. And so this is a source of a lot of the clays that have accumulated here.
Are there, or do planktons benefit mostly from the upwellings, or just it filters throughout the entire ecosystem, like starting from the?
Yeah, not just plankton, but the whole ecosystem benefits from upwelling. So when we talk about fish resources, for example, we'll look at the upwelling zone along South America, and that upwelling zone is a source of very high productivity, and it supports very productive fisheries. So upwellings are often associated with high levels of ocean productivity and high fish populations, some of which are exploited, or many of which are exploited by fishers. Okay, other questions? No more questions? Okay, well, if you're having, hopefully everything is worked out with your groups and everything. I'm sorry, I went a little bit over time. Couldn't find those videos. So we didn't get a chance to break you into your groups, but we'll do that on Tuesday next week to make sure everybody stays in contact. Okay, I'm going to end the class for today.
Thank you.
Thank you.
Sure. And I'll see you all. Have a good weekend, and we'll be back together on Tuesday. Bye now.